Hello, welcome back. Um, so we're ready to start the next session. It's a keynote speech by Leonardo de Moura. It's my great pleasure and honor to introduce Leon de Moura. He's a great friend and one of the, shall I say, main forces in automated reasoning, if I may put it that way. He was the main author of Yikes and Z3, which had a revolutionary impact on software engineering, broadly speaking, but formal methods in particular. And he has now repeated that performance with Lean. And Lean is now used very widely in among mathematicians, which is surprising to widely being used among mathematicians, which is surprising to many outside observers. For example, recently, Terry Tao used it to find some errors in his proofs. So many mathematicians like Terry, Kevin Buzzard, and Imperial, and others are using Lean to check their proofs. And so more in terms of his position, etc. So let me get into that. He's a senior principal applied scientist at Amazon in the automated reasoning group. And he's also the chief architect of the LeanFro, a nonprofit that he co-founded with Sebastian Ulrich. And prior to that, he worked for 17 years. This was starting 2023. Prior to that, for 17 years, he worked at Microsoft Research as a senior principal researcher. And before that, he worked at SRI International. So without further ado, take it away, Leo. Thank you so much.
Thank you very much for the kind introduction. Thank you very much, people. It's not working. Is working? Is working? Thank you very much for the kind introduction today. Super happy to be here. My goal for today is to get you all excited about Lean. Maybe some of you will start using it. These slides are already available. Yes. These slides are available online. I put the address here on the bottom of this first slide. I put many links there if you want to learn more about Lean. But what's Lean? Lean is a pure functional programming language and a proof assistant. Lean 4, especially Lean 4, is implemented in Lean and is a very extensible system, right? This is something that some users love Lean because it's extensible. They don't care about proofs. They just like the language. The main applications are formal mathematics, software and hardware verification, AI for math and code synthesis, and education. Lean has a small trusted kernel, right? And you can also use external proof checkers to check your developments. So Hong Kong and I started Lean at Microsoft Research in 2013, or 11 years ago. Lean is based on dependent stack theory. I have here a small example trying to show why it's all dependent stack theory. Here you have a function f that takes 4 arguments. The first 2, n and m, are natural numbers. The third one is a bit vector called xs. It's a bit vector of size n. You see the type of xs depends on the value of a previous argument. And that's why it's called dependent stack theory. And ys depends on the type of m. And you have the resulting type of this function also depends on the arguments n and m. The structures have the same thing. The fields in a structure can depend on each other. For example, I have a structure called FinNet. FinNet n represents the natural numbers less than n. It has 2 fields, a value of type net, and another field is the types of proposition. And the value of this field would be a proof that the value of val is less than n. Right? Here I have an example where it creates a value a. I define a to be a FinNet of 3. Like it has to store a value less than 3 in val. And bounded, the proof is synthesized synthesize it using a decision procedure. You may ask, what happens if I put 4 there? Well, Lean returns an error. It's going to say that static decides. Statics in Lean should view as proof automation. Is saying, okay, the static decides proof this is false. 4 is not less than 3, as we expect. You can also view Lean as an IDE for formal methods, right? Lean is a development environment for formal methods. Proofs and definitions are all machine checkable. The method community using Lean is growing rapidly, and they love the system, right? And there are many software verification projects at AWS today using Lean. I will talk about 4 of them. And here I have this example of a Lean theorem Mathlib that comes from the Stacks library. Stacks is an open source book at Columbia University about algebraic geometry. Just to give you a feeling on how a Lean proof looks like. I will not spend time trying to explain this theorem. Lean also has a rich user interface. Most users, I think the most popular system for editing Lean files is VS Code, but you can use Vim. Vim is also really good support for Lean, Emacs, and there are others that I don't know, but the main one is VS Code. And most users are going to use this split screen setup. On one part, you have your developments. Here you have a theorem, a definition showing how to append 2 functions, and a theorem proving that if you append 2 functions and compute the length, this is equal to the length of each function if you add them. But the main point I want to make here is that you can click any place in your proof, and your info view, the panel on the right, will show information about the proof state. And this is not just text, this is interactive view. You can hover over the objects, you're going to find implicit information, additional information, you can jump to their definitions. It's a fully interactive vision of your proof. A question we get all the time is, should we trust Lean, right? Lean is a big piece of code, right? It's a big code base, has a bunch of bugs, but the correctness, the soundness of the system relies on a small trusted kernel. You may say, well, the kernel is small. The official one is 10,000 lines, but there are much smaller ones implemented in other languages. But good question. People may say, should I trust this small kernel, right? Well, you do not, right? You can export your proofs in Lean and check with external checkers. Checkers implemented in Haskell, like between 1 and 2,000 lines of code. There are checkers in Scala, Rust, Lean, and so on. Right? And you can also implement your own checker if you want. You can export the proof and implement your own checker in your favorite programming language. We claim that Lean enables decentralized collaboration. There are 2 components to that. One is metaprogramming. Metaprogramming is the ability of using Lean to extend itself. And users do that all the time. They write their own proof automation, they write their own visualization tools, their own custom notation, quick printers. They do a lot of stuff, and I will try to demo some of these examples today. The other component is formal proofs. When you have formal proof, you don't need to trust me to use my proof. You don't need to trust, more importantly, you don't need to trust my proof automation to use it, right? The proof automation is creating a proof, and this proof is checked by the kernel, by external checkers if you want. You don't need to trust people. You can hack it without fear of introducing unsoundness to the system, right? We say that formal proofs address the trust bottleneck, not just between humans, but now with AI between humans and machines too. The Lean community started Mathlib in 2017. It's amazing, grew so much. I mean, nobody would expect it would happen. I was skeptical in 2017. Mathematical library is like software. I strongly believe that to be a good developer, you have to have discipline. It's the most important characteristic of a strong developer. They have to have discipline. And I thought, mathematicians really, they do it. I mean, in my mind, they like to work on abstract problems. And when you have software code, sometimes you have to spend time refactoring, cleaning up, doing a lot of boring things. I was skeptical, but they did it, and the library now is more than 1 million lines of code. In 2018, Mathlib was already 40,000 lines of code, and many limitations of the system were clear to us. And Sebastian Burke and I decided to start Lean 4. We had many goals: fix design problems we had in the language, make the system super extensible, because we saw the mathematicians using Lean to extend itself, but they had very limited ways to do that. We also want Lean to become a general purpose and efficient programming language. But Lean, for his implemented in Lean, is 120,000 lines of code, and almost every single part of the system is extensible. Right? But it is not backward compatible with Lean. And it didn't feel like a big issue at 2018 because Mathlib was 40,000 lines of code, but we didn't expect it to grow so much and became a problem. At the same time, Zulip became a central point where the community gathers, right? There you will find prestigious mathematicians like Peter Scholz and Terence Stahl. You'll find new users, AI researchers like Caillou and Stanislas, new users asking very basic questions, people celebrating projects, discussing specific projects there. And the cool thing people say, if you have any question about Lean, if you post there, you're going to get an answer in 5 minutes. Right? The community is super effective. Then in 2019, we had the first impactful projects done in Lean, the Lean Perfectoid spaces. Kevin Buzzards, in his mind, is saying, if you want to attract mathematicians to proof assistance, you have to do fashionable mathematics. What's fashionable mathematics is mathematics that PG students today are working on, right? And he said, I'm going to formalize perfectoid spaces. This is a hot topic in math. Peter Scholz just got a Fields Medal. He came up with perfectoid spaces. Everybody wants to understand what's a perfectoid space. It's super hard to explain natural language. You have to write a lot. And there's information that's lost there because you're trying to give a concise answer. I'm going to give them a definition in Lean. I'm going to define this concept in Lean. And now it's not about proving anything, but having a mathematical object that we can visualize in many different ways. For example, perfectoid spaces uses something called a page ring. I don't know what a page ring is. You can just click and say, jump to the definition. If you want, you can keep zooming in, zooming in. You can go back to the axioms of mathematics doing that. If you put your energy there, you will understand what a perfectoid space is. It's not like a textbook where people say this step is obvious or this is clear, and you don't know. That for the author, for sure, it's obvious, but it's not for the reader. But here you can keep zooming in as much as you want. In Net Overflow, the question about perfectoid space that is just a link to Lean development is one of the most popular ones. The mathematical library then, because of this project, many mathematicians came to me, and the mathematical library became viral. We had an article in the Wired magazine about Mathlib. The Quanta magazine selected Lean and Mathlib as one of the breakthroughs of the 2020s. And I loved this article. There are many great quotes. Quotes for like really young users, like the undergraduate students saying that I use Lean 14 hours a day. I never get tired. I feel kind of high the whole day, right? And also established mathematicians saying it's a big time investment to build this library. But I believe I'm doing something that others will build on top, like headers that make that saying that I think to really capture the spirit of the community. That's why I selected the quote. Then in 2020, Peter showed himself. He saw, oh, people formalize perfectoid spaces. There are all this buzz about with assistants. He came up with a challenge. He had a new result. A new result he claims the most important result of his career. And he already had a Fields Medal, but he said this new result for me is the most important, and I'm not sure if it's correct. It's too complex. I can't keep everything in my mind. And he challenged the community, not just the Lean community, any proof of system community to formalize the result. Kevin approached me saying, we are going to do it. It may take years, but who cares? We are going to try. But in May 2021, Johan Comelin led a group of Lean users, and they did it. The main theorem, the crucial theorem that Peter wasn't sure, they verified and found small issues here and there. And Peter was really impressed on how quickly people managed to do that. This showed up in Nature, an article in Nature describing this project. In 2022, was fully completed, and we had this nice quote from Peter saying that Lean was really an assistant for him, navigating through the thick jungle speed is, like, making the point that he could not fit all objects in his mind at the same time. If you are interested about the liquid tensor experiment, this project, I strongly suggest you watch Johan Comelin's talk. Johan is the leader, was the leader of the project, and he's a rock star mathematician. But he doesn't know, but he's also an amazing engineer, right? He organized this big group of Lean contributors. He set up the whole architecture, the rate abstraction boundaries, and let people fill the holes concurrently after the whole structure was set up by him. And there was also a big unexpected win. They not just verified the proof, but they also simplified the proof, dramatically simplified the proof. The original proof uses a gadget in mathematics called the Bringe-Line complex. And Johan basically, by using a formal proof, he could analyze which properties of the Bringe-Line complex were really needed for the proof. And then he constructed a much simpler object that had the same properties. Peter was blown away by that because Johan told him he doesn't fully understand the proof. He can understand locally, but not the big picture. Without an assistant, he cannot prove. But because he had an assistant, he managed to simplify the proof without fully understanding the big picture. Then, after this success story, this project was done in Lean. And people would come to us saying, Lean will be like Python. You have Python 2, we have Python 2 and Python 3. You're going to have Lean 2 or whatever. No way people will be able to port Mathlib. But again, the community surprised us again. They managed to port everything to Lean 4. More than 1 million lines of code have been ported. It's just a big coincidence. They finished the ports in the 10th anniversary of the exact same day they finished the porting. And if you're interested about the porting, the efforts that it passou has a beautiful YouTube video explaining, commemorating this accomplishment. Mathlib, they keep really good statistics about the system, about the library. Here we have a graph showing the evolution of Mathlib 4 in red and Mathlib 3 in blue. You see after the port was done, Mathlib 3 is frozen, but Mathlib 4 is growing, right? So it's almost 1.6 million lines of code today. the Mathlib community is in fact how math is being done. For example, here we have a result from Thomas Bloom, right? So he proves, I think, was Erdo's conjecture that was open for a while, and the result was formally verified before it was released. And Tim Gowers is another Fields medalist. Is saying here, maybe this is a sign of things to come. We will change how we do math using formal methods. There's now in the end of 2023 starts learning Lean. And here, the interesting thing that he was really hacking Lean. He installed his machine, he was using and said, no, I want to formalize one of my papers. And he found a bug. First paper he tried to formalize. We found a bug. The paper has a new version with a footnote saying that it was corrected in the formalization using. And if you're not a mathematician, maybe it's not clear, but Tensor is the greatest living mathematician today. It's considered by the whole math community. 2023, we're so grateful for everything that happened that year. New York Times had an article showing how people systems in AI are changing mathematics. We have these events at UCLA organized by Tensor. Quantum Magazine wrote another article and videos about me in the Mathlib community and the intersection with AI. Daniel Bernstein, famous cryptographer, formalizes Copper codes in Lean 4. Wayton Hoare, the creator of Rust, was praising Lean and saying whenever people want to do new programming language research or new ideas, they should look at Lean now. And more importantly, in 2023, Sebastian Drake and I launched a non-profit dedicated for the development of Lean. The missions of these non-profits are address scalability. Scalability is a big deal. As you go deeper and deeper in math, the objects you manipulate are really, really large, right? Scalability is always a problem. Usability, if you want to make this technology popular, the system should be super user-friendly. With automation, you want to reduce the overhead factor. The overheads you get when you're using formal proofs instead of informal ones. We want to support the mathematical community, right? Now the scale of everything is a lot of energy to vote. And we want to achieve self-sustainability in 5 years. We're very grateful for the philanthropic support of the Simons Foundation, the Alfred Sloan Foundation, and Richard Murphy. The non-profits is a great example of a focused research organization. It's a new type of startup for science created by Convergent Research. Convergent had this idea that there are some projects, and this is one of them, that for industry, it's not a good match because there's no clear path for profitability. In academia, it's also not a good match because you need engineers that are there for a long time, dedicated team of engineers. And it's also not a good match for a startup, where the goal is to produce results very quickly to be profitable. But the goal has characteristics of each one of these entities. And today, the Go has 13 people. In the board of directors, you have Jeremy Abigail. He was the first in user, the professor at CMU. You have Adam Marblestone, the CEO of Convergent. And the strategic advisory board, we get feedback from people like Simone Severini. He has a lot of experience creating startups and has many connections. Alex Konturovich is an influential mathematician. He works with Princeton. And Lars Bergström he's the chairman of the Rust Foundation. He has a lot of experience for helping us to transition the Lean Pro to a Lean Foundation, a self-sustainable foundation. 2024 has been great so far. Tensor didn't stop at that first paper. He formalized his new results. And then he got really excited because he set the blueprint of his results, and the community helped him filling the holes. And he said, wow, if I was writing a paper in LaTeX, I would never take a contribution from someone that I never met. But here people were filling my proofs, proving lemmas of my paper, but now that's formal, a formal version of my paper. I never met these people, right? I'm collaborating with people I never met. This technology is enabling that. And he gave a talk this year at the AMS. Was very influential talk in 2024, how to determine proof, result about AI safety using Lean. And Alex Kukurovich launched a new project called Prime Number 3 and Beyond with Tensor. It's also a community-driven project. Tensor last month was interviewed by a Scientific American, where he explains how he sees proof checkers and AI working together for changing mathematics. Another big use in 2024 was LeanDojo. LeanDojo is an AI, and what's special about LeanDojo is that everything is open source. The model is open source, the data is open source, the scripts, the code to connect Lean to the AI, to the large language model, everything is open source. If you're interested in this area, it's a great place to look at, right? So you have a lot of data information. Nevermind is using Lean for verifying smart contracts. We're also very happy to see this kind of application. And just last week, I'll give another talk about the potential for AI in science. Unfortunately, I could not attend, but the talk will be available beginning of August. And my colleagues that attended were blown away by this vision for how AI systems will change how people do mathematics. The main point is that AI is unpredictable, they make mistakes, but proof assistance can catch these mistakes. And also he made the point that Lean Mathlib enabling experts from different backgrounds to work together. I love this quote from his talk saying, it makes you see the essence, proof assistance allow you to see the essence of why something really works. And these are recurrent feedback we get from new mathematicians that are learning to use it. This is only the beginning. I'm listing here some projects. Some of them are fields middle level mathematics like liquid tensor experiment. And there are big ones, really big ones like the Fermat's theorem that Kevin Buzzard started this year. Fermat's theorem has a very simple statement, but the proof is massive. No human fully understands the whole proof. Like Kevin knows really well. His advisor was one of the two people that proved Fermat's theorem, and he was one of the people checking the proof when he was a student. Formalizing Fermat's theorem is also important because the background math that's needed is useful for many different other applications. You also be a way to preserve its results wherever, right? All these different projects use a tool called Lean Blueprints. Right? Lean Blueprints is a way to connect informal mathematics based on LaTeX with formal one. It's used in many of these projects, liquid tensor experiments, CAV's projects, the prime number theory beyond, they all use this tool built by Patrick Massot. The tool allows you to write LaTeX and Lean together. It creates visualization showing which holes are missing. It helps the community to organize itself, right? And creates great visualizations, right? So you have a visualization full of hyperlinks that allow you to jump to the formal version and to even jump to the actual Lean codes, right? You can do all that using blueprints. One takeaway here is that formal proofs enable crowdsourced mathematics, right? Kevin gives a quote from Kevin about the Fermat's theorem project. He was saying, well, the blueprint breaks down the proof into many, many small lemmas. If you can formalize a proof of one of these lemmas, send me a PR. I will be thrilled, right, to do that. Before we start looking, going deeper into Lean and talking AI and Lean, I want to point out the Lean game server. Many mathematicians learn to use Lean using these games. They introduce you to Lean a very step-by-step way. It's very intuitive. I even know kids that learn to prove using these games. There are many more, and the community wants to do many more, and we believe this can really change how people teach mathematics. One takeaway, why all this was possible, right? It was possible because Lean is very extensible. Mathlib is not just math, it has many lines of code containing Lean extensions, around 40,000 the last time we counted. Users can extend Lean using Lean itself. They can browse, access all internal data structure. They are treating math as data. They can manipulate and transform. We wrote Lean for in Lean to ensure people can extend most parts of the system. And they do it. Like a few weeks ago, David Renshaw, he wrote a package for animate link groups. This link code, he wrote a package in Lean that exports a link group as a Blender animation, right? It's really great. If you watch his YouTube video where he presents the project, I was blown away. He impresses me many times. He really uses all the extensibility to do really cool stuff with it. Another example is Silene, the scientific computing assistant by Thomas Driven at CMU. Is a framework for scientific computing. You can solve differential equations, do optimization, machine learning. And then you can also generate animations. You can define functions and he put extensions for proving the functions are smooth automatically, for showing the functions to compute derivatives. A lot of automation is done using this Lean extensibility. Everything is implemented in Lean. We also have proof widgets. We talked a little bit about the info view. I said info view is interactive, but these two users, check and ads, they went one step further, allow the users to define their own visualizations in the info view. The really cool stuff is that the codes on the left panel is defining the visualization and defining the red black trees. Is writing the code and the visualization in the same file, super convenient to do. And you get the visualization in the VS Code, in the info view on the right panel. You can visualize mathematical, in this case, you're visualizing red black tree, the computer science data structure, but you can visualize category theory diagram. The sky is the limit. They have many examples. And the Mathlib now uses this package that was developed by them. Now, let's switch gears a little bit to AI and how there are many groups using Lean for AI for mathematics. It makes sense, right? Large language models are amazing, but they hallucinate. Here is a simple example from Suho sent me. If you ask all of these models, it's amazing. They all create a crazy proof for something that's clearly not true. You ask them to prove there are infinite integers to two distinct integers. Anybody knows this is not true, but they come up, every single model comes up with a crazy proof why this is true. Let's go over some applications of Lean in the AI space. OpenAI built GPT-F, right? They can solve some math Olympiad problems using Lean. And I think the example here connects to the keynote yesterday about talents. The main point OpenAI made is that the model came up with these terms, square root no neg, b minus a, square root no neg, c minus b. The AI came up with this part. And then said, okay, now that we have these terms, use this NLRV, nonlinear arithmetic decision procedure. Actually, it's not a decision, it's a partial decision procedure. Give these three extra facts, and now the proof is done. The magical part, the AI is doing some of the talents. It's combining with automation, standards proof automation that we developed at CAV with terms that have been synthesized by the AI. Meta also works in this area. They developed a technique called hyper-throughput search for new term proving. They got inspirations from AlphaZero, and the idea is to suggest static delivery, right? They would do a tree search using a large language model to guide the search, and they will suggest statics that can be applied to specific steps. And you can just click the suggestions and click them. Right. LeanSAT is an auto-formalization tool that you can write something in English with a code action. You can ask the large language model to convert what you wrote in English, formal language. Right? You see the quick fix is the code action. And this is a package that's available online by Siddhartha Gadgil, a professor of mathematics in India. We have also Harmonic, is a startup that's using Lean to build a mathematical superintelligence. I put it here because I found funny. Some of the mathematicians came to me saying, wow, my students in the past, their path was academia. They all were all going to academia. This is the first time there are startups, Silicon Valley, recruiting my students to work on some projects in Silicon Valley. And I found it was really cool. Now, let's see. I want to make a quick tool of Lean. And I think the quick tool will convince you with new ideas on. Suppose that you want to design a new language for specifying protocols, and you want to verify this protocol. Maybe Lean is a good platform for developing this language. This is a toy example. It's a toy example that David Christiansen and I used in a summer school 2 months ago. And I have the link here for David's repo, the whole development. And it's a great example. If you want to create your own language for doing something, and you want to verify properties of this language, you want to connect to automation, it's a good platform. Let's see how this example is structured. First, you define a language of inductive type that represents expressions in a simple imperative language that manipulates with vectors. You have constants, you have variables, unary and binary operators. This is an inductive data type, right? It's a recursive one. Then we start defining a syntax. Lean has an extensible syntax. We can define a syntax for writing terms of this expression language or this simple imperative language. Then we use macros. On the bottom, we have a macro system that allows us to convert the syntax into elements of this inductive data type that we just that's defined on the left-hand side. Then we do the same thing for statements. Then you can write the factorial function in this imperative language in the middle of your link file. You can have code that's very readable in the middle of your link file. Suppose that you define a language for specifying protocols, you can do the same. You can have in the middle of a link file, which is nice syntax for your programming language. Then we start showing usual stuff. Oh, let's write a constant folding function that converts expressions to expressions and statements to statements. It's just optimization, right? So if you have 2 plus 3 replaced by 5, if you have if of 0 of then A else B, you reduce to B. Applying very simple transformations as an example. Then we give the semantics of this language, right? We're using big step operational semantics. The environment here is just a mapping from variable to values. And the big step is a relation, a ternary relation showing the environment before. You execute the statement and after. right? Is the usual what you would find in any textbook. Then we prove the optimizer is correct, right? So we have optimizations, okay. If whole and whole prime are the environment before and after executing S, if you optimize S, you get the same whole and whole prime, right? Just showing the optimizer, the result of the optimizer matches the semantics we define it. It's not going to disrupt. Then we write an interpreter, right, in this summary screen. And the students play with it. We wrote an interpreter and we prove the interpreter to be correct. If the interpreter gets an environment, a statement, and a number of stats with a new environment, and it will show that it satisfies the environment's whole prime and the statement as they will satisfy the big stat operational semantics relation. I'm not putting the whole book here, just a few the glimpses. And then comes the most interesting part. We wrote in this new imperative programming language, pop count. This is in the middle of the link file. You have the pop count. Pop count is this bizarre algorithm for counting how many bits are true in a word of 32 bits, right? Many of us have seen this book, Hackers Delight. And one of the examples is this pop count. And you look at it, I say, is this really correct? It's so crazy to me. Then we wrote PopSpec. PopSpec is just a recursive function in LeanSAT that counts in a really natural way the number of true bits in a bit vector of size 32. Then we want to prove that pop count is correct. Well, how do we do that? So we say, well, exists some environment. If we start with the initial environment, we execute pop count for 8 steps, we get a new environment. Then if we access the value X symbol, we get the same results of running the PopSpec program written in LeanSAT. And you may think, wow, this problem is going to be complicated to prove, but in LeanSAT, just 2 lines of code. The first one is the simplifier. The simplifier in LeanSAT can be used to encode functions, to apply theorems that we proved before, and so on. And then we call a bit vector decision procedure. Basically, simplifier is just a preprocessor. It's eliminating all high-level concepts, relations, eliminating all that and getting a bit vector problem that we call, and then we call the BB decide procedure that invokes the verified bit blessing. And you can inspect, if you click before BB decide, you see the states of your proof state. You see what the simplifier produces, and we can hover over all the elements in proof states. BB decides is a verified bit blaster. It has been developed by Aaron Povink. He works for the LeanPro. It uses the LRATS verified checker by Josh Krohn. He was my intern at AWS last year. And Siddharth and Alex contributed with many background theorems that were needed to prove that the bit blaster is correct. You can use any set solver that produces LRAT proofs. In our case, we use CAV. This package provides many different tactics, including the DT size. And it works as follows. First, a preprocessing step using Lean simplifier. This is a very extensible simplifier, but it gives you strong guarantees, right? It produces a certificate that guarantees the simplification is correct. This is important in bit vector solving. When I was working in Z3, many of the bugs in the bit vector decision procedure in Z3 were being preprocessing, right? To apply some preprocessing step that was incorrect. Then we use reflection. We convert the lingo into an expression, an inductive data type representing the bit vector terms. Then we map this to an AIG, right, module that has been verified and has a verified CNF translator. Then we call CAD-CAL. CAD-CAL comes with LRAT proof, and it's verified using the LRAT verified checker. Right? We're not compromising soundness. And it has completely implemented in Lean. The only part that is not implemented in Lean is CAV. The connection that accesses the state of the Lean goal and converts it to its vector expression using the indexed data type we define as in LeanSAT is all implemented in Lean. I don't want you to look at the details here, but just give you the idea how it looks like in this connection. Then here, this is the most interesting part. A 5VP expert is something that gets elements of this type with the logical expression, right? Is an inductive data type defined in Lean and an LRAT certificate. And it just returns true or false, this function. True, it means that LRAT set is a certificate showing this bit vector logical expression is false. This is unsatisfiable, sorry. How it works is we apply this blaster with some step called relabel nets. It's just massage the expression. We convert to AIG. Then we check if the certificate for the result of CNF is indeed the certificate for this that the CNF is unsatisfiable. And we have a theorem showing that if it is the case that you verify the expert for a bit vector logical expression and a certificate returns true, the bit vector logical expression is unsatisfiable. This main theorem is just 6 lines of Lean code, but it uses a lot of background, lots and lots of results that have been proven to get to this point, including a proof that the LRAT proof checker is correct, like the verifies cells. If it returns true, the CNF is indeed unsatisfiable. And another cool thing I thought was also good way to highlight a feature. I mean, it's an idiom, it's not a feature. It's an idiom that's used in many different places. It started with the math community adding question mark patterns, variants. For example, you can say BV decide question mark. It's like BV decide, but it has a code action associated with it. It tells you, oh, you can replace BV decide question mark with BV check that takes a parameter LRAT proof. If we do that, it changes your proof like to BV check. But the cool thing now is that you do not depend on CAD-CAL anymore. It created a file with the LRAT proof. You can put your file in your repo. Now you can compile this link file without using CAD-CAL anymore. And you save time. You don't have to keep running CAD-CAL over and over again. You run it once, get the LRAT proof, and do this simple click, and you now have a proof that's much easier to compile. Which is idiom is used everywhere. The simplifier has a similar feature. ASOP, that's a white box piece of automation that's very configurable, also has a question mark option variance. And the idea is always like, if you have a piece of automation that does a lot of search, maybe it's a good idea to isolate, to produce some more compact proof that will not do search over and over again when you're compiling your files. Now let's use the last 2 minutes to talk about projects at AWS. At AWS, we have the automated reasoning proof that was created by Byron Cook 10 years ago. If you want to understand how automated reasoning is used at AWS, I will focus only on the Lean part. I would strongly suggest you watch this talk, The Business of Proof by Byron. It's a really great talk showing how automated reasoning became so popular at AWS. I will focus on 4 projects. There's a blog post coming soon about giving additional details about these projects, and there will be more projects being open sourced in the future. Cedar is a policy language for permissions at AWS. The Lean model for Cedar is available online. You can browse and inspect it. Cedar is becoming industrial standard. It's not used just by AWS, but it's used by many users, different customers, and other big tech companies. And how is Lean used there? Lean was used to build a model of Cedar and put many properties about the language, like soundness of the type check that has been improved in Lean. But Lean is not run in production at this point. There is a Cedar implementation using Rust, right? And what they do, they use random consideration, differential testing, to check whether the Rust implementation matches the model written in Lean. The main takeaways for this project is that Lean is a full feature. This is a feedback they gave us. Lean is a full feature programming language, has fast speed checking and runtime, and in a brilliant way to build the models and things. You can learn more about Cedar in this blog post written by Kesha and Nina Torlak. They will give you many other takeaways and how to lean in your own projects. Tensor, the open source library that formally verifies differential privacy primitives. It's now in production in the AWS clean rooms, right? It provides fast and sound sampling algorithms. To the best of our knowledge, this is the first verified implementation of discrete Gaussian samplers. And the cool thing that it's not just verified, it's twice as fast as the previous one that was not verified. This project was led by Jean-Baptiste Tristan. And one cool thing that's the mathematicians in the Mathlib community, most of the time they feel like software verification is just lights, mathematics lights. I don't think they want to offend me too much. They say, no, what you're doing this light stuff, it's not really math. But when they looked at Jean-Baptiste's project, they came to me and said, wow, this is really deep mathematics, right? To prove these discrete samplers, Jean-Baptiste had to use Fourier analysis, number theory, topology. Another project is LeanSAT, the symbolic simulator for machine code programs. It's led by Gilles Goel. It's also open source and under active development. The goal there is to check crypto written in assembly language, right? For AWS matters writing assembly, right? We really care about performance. And Lean uses a specification language for ARM, right? And for modeling cryptographic protocols. And the cool thing here is that they are using this mixture of automation. They use the BG decide tactic a lot, but if it doesn't scale, the set solver is timing out. They have the opportunity to interact with the massage the field before calling the set solver. Right? So they are not blocked by the complexity of the problems we are trying to verify. And finally, we have AIV. It's led by Subho Kong. It's nice. I don't know if you remember, but in the beginning of the talk, I said in 2013, Subho and I started together, and it's great now that he's using Lean again in leading a project at AWS. It's a collaboration with the Technology Innovation Institute. And the goal is to use AI for math and math for AI. What do they mean by that? AI for math means you want to use large language models to improve automation, to suggest that to users, to explain users when they have an error message they do not understand, try to provide user assistance. Math for AI is about using Lean as a machine that can generate synthetic data sets that are correct by construction. It is a big deal for machine. To learn more about Lean, I have many links to the website, to Twitter and Mastodon. You can try Lean online, right? You don't need to install Lean to try it. The community website has lots and lots of information. Many courses that have been taught using Lean are available there if you're interested in education. You can engage with the Lean community in the Lean channel. Again, everything is available. My slides are available online. All the links, you can access the links. You download just my slides. concludes means efficient programming language and proof of system. It eliminates the trust bottleneck. It enables decentralized collaboration. It's super extensible, right? And you can add extensions without fearing. You have to do it without fear. There's no risk of missing soundness. We strongly believe the Mathlib community is changing how math is done. Lean proofs are maintainable, stable, and transparent. If you look at the blog posts and talks by Leonardo, like she has a lots and lots of data showing how easy it is to maintain the proof now that she's using a proof of system. And we believe the flow model has been instrumental to supporting it. Right? We would not be able to keep the project going without the philanthropic support we got for the lean flow. The last sentence I want to say, we try to summarize all the feedback about mathematicians and lean users. That it's not proof of systems are not about proving, but also it's not just proving. It's also understand complex objects and proofs, right? Getting new insights. We get this feedback all the time. I got a new insights when I use a proof of system. It's about navigating complex objects that are beyond the cognitive abilities, right? Thank you very much for your attention.
Two quick questions. Do you have plans to verify the lean kernel? And what about speeding up things like loading Mathlib?
Well, the lean kernel, actually, Mario Carneiro has a package called Lean for Lean. He wrote, the checker that's implemented in Lean was by Mario. And one of his dreams is to verify this kernel. Okay.
Quick technical question and philosophical question. Technical. What is the underlying set theory?
Excuse me?
What is underlying set theory of automatization? You say everything goes back or down, you can zoom in. So you have to be able to zoom in all the way to set theory. Which set theory do you use?
No, yeah. There is a model of Lean. Lean is based on the calculus of inductive constructions, but there is a model. Turns out it was Mario again. He wrote a model, set theory for Lean. He uses inaccessible cardinals. Set theory plus inaccessible cardinals. And this was his master's thesis. And it has been checked by many mathematicians. Like Tom Hales was the first one to check the model.
And what about open set theory? The dependent of actual flows from ZF.
Yes, actually, Jesse Ham, since the independence of the continuum hypothesis hasn't been done, he was actually Tom Hales' student. He did a few years ago, independence of continuum hypothesis.
More philosophical. There have been probably millions of lines of code trying to codify mathematics in HOL and in POR and in Isabel, and who knows what else. How can we not let that cultural heritage just be lost? Let's say if the world moving to Lean, somehow suck in everything else has been codified in mathematics.
Yes, yes, it's a great question. And we also should keep in mind that also those of the system, they all die. Actually, one that you can here, but also of the systems die, and we should be prepared. Lean will die one day too. There will be other. We need to build technology that allows us to port the libraries to new systems. Right? This does not exist today. Right? We are even new programming languages are popping up all the time, and we're implementing the same things over and over again. It's not just a problem of formal mathematics, but also software development. This we still, there are hopes this will change.
It's quite possible now that people will publish the theorem, they'll publish the Lean code.
Yes.
And then in 50 years, people say, oh, we can do anything with it. It's like a cuneiform tablet.
Yes. I agree with you. But the point is that there are a lot of people working on technology, but translating, because now that's in Lean. Lean Lean matrix data now that can be manipulated. Like you can write, in principle, you can write translators from Lean. We hope this will happen to be able to link to a new system that you
But I want to go talk to John Harrison, go from HOL to Lean.
Oh yeah. We talk. John Harrison is my colleague. I mean,
I
he
know,
talks about
so I
that.
mentioned his name.
Yeah. Yes. We talk, but getting like at the assembly level, this is feasible. But getting it at the level that's usable is a different story, right? I mean, even Coq and Lee are much closer than all lights and Lee. Even going from Coq and Lee to Coq is a challenge today, not because of the foundations, but because of all the infrastructure you have on top. The mathematicians rely a lot. The proof automation, the text framework that automates your proofs, the elaboration that fills the holes you didn't specify, all that matters to get everything working in a way that's usable by the users is a challenge. It's like when people translate Java code to C# automatically. Yeah, it compiles, but you cannot maintain it. You cannot use it effectively. You have to sometimes write a wrapper around. But this is an active area of research. People are strong. A bunch of people believe AI will help do that. AI is really great at translating between languages. Yes, we're all concerned about this problem. We believe we will solve this problem.
Question. Is it the case that every kind of mathematical reasoning that has ever been used in any proof ever written can be expressed in Lean? Or are there some fundamental limitations to the logic, some sort of mathematical types of reasoning that just can't be expressed?
Yeah, I think the question is a great question, but I think what actually happens is how convenient it is to be Lean, right? Sometimes because if you have to do a bunch of encoding tricks to express, it becomes too inconvenient. I mean, you lost the main points lost in the translation to me. I think right now we're trying to push the limits. The theory version project was one that was trying to push the limits. In the area of mathematics, not sure if we can do in a proof of system. They succeeded. In 2 hours, we were really surprised that they succeeded. But we are going to see more and more projects trying to push the limits and see which parts of mathematics can be done in a proof of system like me. What kind of encoding tricks you have to do to understand.
Thank you for the talk. So I was inspired by the example you showed with this equivalence between a program and its optimized version. Why not use the same approach, maybe a translation validation for the CDAR project, where you could, instead of having to do the differential testing, could Lean not be used to do the translation validation there?
Oh yeah, but the challenge, the production version implemented in Rust, right? It's a massive project. Just in the semantics of Rust would be a massive project. This may be one day, it will happen, but not today. Another thing that people are considering is using Lean production directly, right? You don't have to only one, right? But this also takes time, right? Lean is a new programming language. If something happens, the system is down during the night, we need to have people on call to fix. If it's implemented in Lean, this person will have to know Lean, right? Lean's not to Rust. Rust has a much bigger community.
Yeah. Hi. So can you tell us a bit more about how it is to use Lean as a programming language for general software development? How is it the developer's experience compared to Haskell or ITRIS or similar?
Yes. We did some comparisons, performance comparisons a few years ago, Sebastian and I. May not be up to date from 2019, but in that comparison, we compared with Haskell or Camel PolyML, and Swift. And Lean outperforms all of them in the benchmarks. Of course, the benchmarks we have, we had in the paper were about symbolic reasoning, program transformations, things that are lean, very lean specific. But we believe the performance is quite good. If you go to Elena's blog post, Kesha, they praise a lot the performance of the code. Nico Makasaki is the lead developer of Rust, was also impressed by the performance. When he approached Sumo and myself at AWS, he said, could you tell us details of the implementation, what we're using the data structure? He was impressed with the performance.
And a second question, if I can. So suppose I develop a reasoner or some software for the automated reasoning, and I want to output proofs to be checked by Lean. Does it have an API to use to build proofs, or do I have to output some text format, or is the tool chain for integrating with other software?
Yeah. If you wrote in Lean, it's super easy, right? If you just write in Lean, you have to use a point function interface. It can be done, but it can be also painful, right? Especially if you have to translate data structures. If you go to the Lean manual, we have a section on point function interface. CEDA is also a good example for looking at how the point function interface works in Lean. They wrote for doing the differential testing there. It's not shooting independent programs. The Rust program is calling the Lean program and checking, and you see all the glue code they had to write to connect to the system.
Yeah, so one of the most exciting things that I got from this talk was how Lean is useful for scaling mathematical collaboration. And you talked about that from a trust perspective and how essential it is to have a way to collaborate without having to trust. I'm also curious, though, about from an efficiency and resource perspective, in a future where Mathlib is 100 million lines of code and the storage required to hold it is, I don't know, 10 gigabytes with all the extra proof data. Are you worried about the scalability of the underlying kernel in that space, and what are you going to do to overcome the challenges there?
Yeah, it's a big too. I mean, one of the motivations for having the flow was exactly a mathematician that came to the community asked the question, what will happen when Mathlib is 100 times bigger, we have 100 times more users, 100 times more PRs, right? Yeah, we're super concerned about that. Not even about the automation, so that we haven't scalability, but just the CI. It's like a massive project. It is 100 million lines of code. It's bigger than Linux, right? This kind of project has a team of people just making sure the CI is working. Our plan there is to provide tooling to break Mathlib. It's a single repo. Like what we are working, our goal is to provide tooling. I didn't talk about reservoirs, our cargo, not cargo, crates.io. We have Lake that's the equivalent of cargo. We want to also provide Johan Komelin now that's led the liquid transfer experiments is working for the Lean Pro, and he's building tools for helping breaking dependencies in Mathlib. But because one of the drawbacks I have each community contribution, that sometimes everything depends on everything else. And having tools for breaking dependencies, linkage to help people to break things into smaller things. And eventually we hope we will have an ecosystem like the Rust ecosystem where you have many tiny packages instead of monolithic repo. I'm not backing the monolithic repo. Many people in the community, they are right. Success of Mathlib mainly due for the fact that it's a monolithic repo, because we did not have tooling at the beginning, and we still don't have good tooling for breaking projects apart. But we really hope we will have, that we are working the whole goal is working on making sure that we will exist and we will enable people to break as well.
I guess maybe a short follow-up. I mean, the alternative approach is sort of the Google approach, where you integrate your build system and your repository system. And do you think that approach is a non-starter in this kind of open world, or that should also be considered?
Yes, yeah, it's funny. Many people, when we talk about breaking things, people come, oh, Google has a monolithic repo. I say, well, but to contribute to this repo, you have to work for Google, right? And the other thing, there's a big team maintaining this stuff, right? We don't have this kind of info.
Additional questions? Hi, thank you for talking your work. So can we elaborate a little bit more about the proof automation you have? Do you have a new idea? Because you don't have the interpretive components that LTAC can call, which can be customized syntactics. Do you have any new thoughts about that? Because I've seen something like the question mark operations that can do some associations, or can we do some more support some other proving strategies like perfect contradictions where we're or other things.
Yes, you use Lean for everything. I mean, you use Lean for writing proof automation, right? There's no LTAC or things like LTAC. You write Lean code for doing your own proof automation. You can use as examples. If you're interested in learning more, you can look at the LeanSAT implementation. You can look at ASOP. ASOP is similar to auto-attaching in Isabel, and there's something like that's in Correctness. You can look at these implementations that were all written in Lean to see how to write proof automation that you can write. The short answer is you will be using Lean for doing proof automation.
Thank you.
I have a follow-up question. The lean and lean writing of proof automation. Does this have facilities for parallel computation? I mean, you worked with AWS, so you could brute force on 10,000 cloud servers some proof attempts.
Yeah, great. Lean has primitives. I mean, for parallelization, we have threads, task. What else do you have? Promises with all available in the Lean API implementation. The elaborator now, we have an incremental elaborator. Like if you change your proof in the middle, it will not start from the beginning of the file, but from where you change it. And now we're actively developing, actually Sebastian is leading this development to compile the same file in parallel. For the CI, it's relevant because you have the file granularity works really well. But for interactive use, compiling parallel is super useful, right? It gets a more responsive system, and this is what to come like in the next few months.
Hey, I have a question. So, has anyone tried to formalize computability theory or complexity in Lean?
Yeah, I spoke last year when I gave a talk at Simon's Institute at Berkeley. I met a group there that were interested, but I didn't see much progress in this area, but I would be really excited it's happening in the future. But I think the main takeaway from that is you need a community. I think the first step is to build a community. Don't try to do it by yourself. Try to get more people in the bandwagon. Use the power of the community. This is the main takeaway from the main community.
One last question. If I were to write a SAT solver in Lean, would it be KISSAT or the latest
Yes.
solvers?
Yes, I don't know. I mean, who actually implemented a SAT solver in Lean. It's not a high performance one, but he proved it correct. It's called SAT. There is a verified SAT solver in Lean.
Thank you so much.
Thank
Thank you
you.
for such a great talk. Thank you.